can introduce myself.
Okay, guys, so thanks for showing up in person. This is the second to last talk in this series of the IBM Illinois Discovery Accelerator this semester. We're going to be back in spring, but we have the pleasure to host Peng Wu today from Meta. And Peng Wu is, I have to read this because it's not my field, unfortunately, but Peng Wu is the engineering manager of the PyTorch compiler team at Meta. So anyone who does machine learning essentially profits from her or benefits from her work. Dr. Wu spent over a decade at IBM Research, working on many aspects of programming systems, and then found the Programming Technologies Lab at Huawei. And you led the growth there for 6 years?
Yeah.
Wonderful.
Yeah, we started with like 30 people to like 400 people.
Unbelievable.
Until something happened, so.
That's a different scale.
Yeah.
But at Meta, now she's supporting the team search for the right compiler solutions for PyTorch for like the last 4 years.
The last 4 years.
Okay, yeah. So this is good because Peng is a nice connection to the institute. So she was at IBM for a while, and she holds a PhD degree in computer science from the University of Illinois Urbana-Champaign. So you know, if you're embodying the institute, I'm looking forward to your talk. And Peng will talk about the PyTorch compiler. Yeah. Peng, please take it from here.
Thank you. Yeah, actually, my first graduate school year was in CSL. I still remember the feeling of in this building. So it's great to come back after more than 25 years. All right, so welcome everyone showing up early in the morning. And I just want to say that I'm a compiler person. I'm more of a compiler person than an ML person. And this talk is really talking about compiler for PyTorch. And I want you to, I tried not to go too deep on the compiler technology, but I do want to tell a story, which is what my experiences are for the last 4 years, looking at a very interesting arc of how we find our place as a compiler team in this very, very popular machine learning framework, PyTorch. So that's why the subtitle is The Journey of a Useful Compiler and an Industry Perspective. So whenever I tell people what I do, people confuse between compilers that's designed for the hardware, which is actually a lot of the academic research, also startup, are about, and compilers for ML frameworks. So I always say like there is the ML framework and there is the hardware, and in between there is the system technology. So I would classify the PyTorch compiler as the ML framework compiler. So it's occupying the upper part of the stack as shown in this picture. And then there's always a need for a compiler when you build a ML accelerator. So that's the lower part of the stack. And in between, there's always some overlap between the framework compiler and the hardware compiler. But what I want to say is, I mean, this is usually what I show. I draw this picture for MLSys like maybe 2021. But there is actually something wrong with this picture. I'm asking the audience, do you see anything wrong with this picture?
Yes, people in the room should have answers to that question.
I see puzzle looks, so I'm gonna review here. This picture has a compiler-centric view. You see like the big part in the center is ML compiler, but in reality, actually, compiler may not be in that picture. So I just want you to remember that what's wrong with this picture. I'll get back to that. So let me roll back to 2018. So actually, PyTorch started as like an intern project, maybe in the time frame of 2016, 2017. And the first release, PyTorch 1.0, was in May 2018. And this is a release note. It says that, okay, PyTorch launched over a year ago, so that's kind of 2017. And the speed and productivity and ability to support cutting-edge AI models, such as dynamic graphs, quickly make it popular and important development tool for AI researchers. So I highlighted a few keywords here. Dynamic graph is actually just a library. It's just like an interpreter. There's no graph there. Productivity is really about development speed. So what's really interesting here, I want people to have a perspective back then. So 2018 timeframe, I would say TensorFlow is still #1 ML framework. And there is also other ML frameworks. I think TVM has started, MXNet, and different versions of Torch, Lua Torch. And PyTorch was relatively late into the game, 2017. So what happened here is at the time, there is a conventional wisdom about when you design an ML framework, performance is number one, and graph mode is how you get performances. And it seems there is like a tension between like, do you choose graph mode or do you choose ease of use? And to give you some perspective, actually, at the time, PyTorch made a very bold product design decision. So all the other frameworks were designed by system people and or slash compiler people, and they choose to. Could people mute because I hear some noise coming in? Thank you. So they choose to go with this graph mode design, and the graph mode design also impact how people author their models. So for example, TensorFlow, especially 1.0, you have to build a graph and then you launch that graph. And then the compiler would do all the magic and then map to the hardware to execute it efficiently. And that seems to be the conventional wisdom at the time. So PyTorch at the time actually made a bold choice, and we decided that we're just going to design it as a library, as an interpreter. There's no graph, even though we call it dynamic graph. Later, we call it the eager mode. And our consideration is really ease of use. And also behind that, we're really targeting a very different demographic. So basically, we're targeting ML researchers versus like production engineer, where they convert models into run into production systems. So let me show you whether that strategy works. So since 2018, PyTorch 1.0, so we track the percentage of paper using code and how many of them are writing papers and demonstrating their latest ML technology using PyTorch. So this is one way of tracking adoption on the ML researchers. As you can see, we started from 30% to almost like a year and a half later, we crossed the bar to 50%. So apparently that strategy has worked. And today, actually, the PyTorch is famous for being very friendly to ML researchers. And today, if you watch out for the cutting edge of ML, for example, generative AI or LLMs, I would say probably more than 90% of them are using PyTorch to program. So, but there is one catch over that. So number one, it shows that for PyTorch 1.0 to be successful, there is no need for graphs or a compiler. I'm just validating the point of pointing out what's wrong over there. But also we do see that what makes PyTorch really beloved by ML researcher also make it hard to introduce graph mode or compiler. So let me explain why that's the case. So number one, of course, because we didn't design with graph in mind. So then you have an interpreter, then you have to figure out how to get the graphs. And it turns out to be very challenging. Number two is because we didn't have graph mode for 1.0, so the library design, we introduce a lot of tricky or complex semantics like view to save memory copy when you write in the library mode, or in-place updates, gather and scatter. All of those provide flexibility and allow you to optimize your code without relying on a compiler. And that actually makes it a lot harder compared to other frameworks with very clean, simple, primitive ops to optimize by the compiler. And also, as a consequence of that, we have a very large ops surfaces because that's our primary way of optimizing eager performance. So PyTorch did have many attempts before at introducing graph mode, and this is actually what I have witnessed for years at Meta, although this effort has started like way before I joined. So we have TorchScript, and actually we have two modes of TorchScript. One is the JIT script mode, and the other one is the tracing mode. And both have cons and pros. Some are best effort, but if you produce a graph, it's correct. And others always produce graph, but may not be always correct, which might seem very strange for a compiler person, but that's true. And lazy tensor, that's our last attempt before the technology I'm introducing, where it's always producing graphs and it's always correct, but there is a high overhead. So then let me introduce PyTorch 2.0. So this is actually the keynote announcement for PyTorch Conference 22. And in fact, in this talk, I'm gonna show you the arch of PyTorch compiler through the different themes we have from 22, 23 to 24. So this is announcement note for PyTorch 2.0. This is the official release, although the OSS announcement was December 2022, just to show that people like this technology is coming, you can try it out as nightly, but the real release was in March 2023. So that's roughly 5 years after 1.0 release. And here we talk about eager mode performance, eager mode development and user experience while fundamentally supercharging how PyTorch operates at the graph level under the hood. So remember that two things I showed, there's this dichotomy between ease of use and graph mode, and this is the first time we put them together in one release node. So let me introduce the main API, which is what we call our product for 2.0. And this is simple API called Torch Compile. And you put your model in here and you specify a backend. The default backend is Torch Inductor backend. And then we introduce three modes. There is a default mode and there is a reduce overhead mode, which will invoke photographs and especially helpful for models that are smaller and it's overhead bound, especially for GPU. And then we have an auto tune mode called max auto tune. All right, so just keep in mind this is the user interface. So what we're trying to do is not to change the way PyTorch users program their model. So you will program your model as before, and then you add this roughly this one-liner change where you would compile the model. This would return another model that's callable. It's already compiled, and then you invoke that compiled model, and that's all you have to do. All right, so let me give you some intuition on what is underneath Torch compile engine. So if you ask me like, oh, we're gonna revolutionize PyTorch performance by a compiler, like what would be the key technology? For me, who has like my entire career is on optimizing compiler, I would never have thought it's a front-end technology. But that is the case for PyTorch 2.0. So if we have to say like there's one thing that made 2.0 possible, I would say it's how we figured out to have an out-of-box graph capture technology for PyTorch. And this component is called Torch Dynamo. So let me just give you some intuition of what this thing does. So to give you a little bit of code example of how we use compile, so one way of doing that is to do a decorator. So this would tell the compiler to kick in to compile this toy example. And note that we specify another backend. So the default backend is the optimizing compiler, but for illustration purposes, I'm just writing like a custom compiler, which the only thing it does is take in a graph that Dynamo captures and then print it out as an IR. So this also shows how easy it is to customize it for your own thing. You could connect it to your own backend compiler for your own accelerators. Everything is programmable at the Python level. So, and with that, actually, basically, then you call toy underscore example, the system would automatically kick in to invoke the compiled version. So how did that happen, right? So the number one consideration we have is let's not introduce yet another C Python, whatever variation, right? We don't want to change the execution environment of users. And luckily, Python has this very powerful feature called PEP 523. That's an API that allows users of C Python to take a PyFrame object, do something about it, and stuck it back, and then invoke. So this is basically the standard mechanism we're using with C Python. Beyond certain level, then you just don't have to change your execution environment. And everything that's dotted is the part that we added, which is basically the implementation of Torch Dynamo. Just briefly introduce what this does. So once we get the PyFrame object, we would do bytecode inspection to capture graphs. In fact, we are not necessarily only capture one graph, we might capture several graphs. This is actually a unique feature of Torch Dynamo. And we capture graphs, and there are also something called a guard to test whether these graphs are still valid. Because when we capture graph, we might have some runtime information that's being used there. And to the right, once we have these graph fragments, and then we call this compiled function here, the backend compiler we have, and that produce a callable, which is a compiled function. It could be a binary, it could be a Python thing, whatever, as long as it's callable. And then the behind the scenes will make the PyFrame object to actually invoke the optimized version. And that's how the whole contraption works. But from user's point of view, they really don't have to worry about what's happening underneath. So actually the key of capturing graph for a PyTorch compiler for optimization versus a Python compiler for optimization is you want to capture enough of the PyTorch semantics, like the TensorOfts, but you don't want to capture all the Python semantics because then it's impossible to optimize. So, to want to show you that this is very practical, we do capture a lot of the tricky semantics of Python that we often see in model processing, as well as all the PyTorch ops. So this shows you, like, for example, something very tricky like control flow or lambda or function calls, comprehensions, closures, all of these things we do capture, but there are a lot of things that we also ignore. So I think this one actually is the one that will really give the intuition of like, how come all our previous attempt of capturing graphs didn't quite work out with all kinds of problems, but this time, what's the magic in Torch Dynamo? So it's actually very easy to understand. So number one is we no longer target on only full graph. Of course, if you get full graph, you get better performance. We're happy about that, but it's also okay to have partial graphs. And partial graph gives us the ability to skip things that we don't want to capture. So for example, if you have like a logging function in there, right? So in that case, like we don't know what this print or this call is doing, and we'll just like graph break over there. And that partial graph would be optimized, and then the logging part would fall back to eager to execute as a regular Python thing. And then after the logging function is done, and we come back and then start to capture the next partial graph. So this is the key to making sure that user don't have to change their code. The system would automatically enter into GraphPatcher, get out of it, fall back, and then enter again until we reach the end of execution. The second feature of Torch Dynamo is we are generating guarded graphs. I don't think there is this concept of guarded graphs before PT 2.0. And this is because of the unique way we're capturing graph by inspecting the stack. So we're using some aspect of the runtime information. So, and sometimes it might be a control flow path that we're taking, right? So then we need to remember that that control flow needs to be true for this graph to be valid. And that information is called a guard. And we do have all kinds of guards there. And so these guards allow us to produce graphs that are always valid. And once you have guards, you also need to have a way to validate those guards at the runtime system. And if it fails the guard checking, then there should be a way to just-in-time recapture. So basically, partial graph, guarded graphs, and also just-in-time recapture are the three key elements of making Torch Dynamo both sound and also does not require user intervention to produce the correct graphs. All right, so that is the Torch Dynamo piece. And I want to just touch base on like another component of the front end, which is called AOT AutoGrad. And this is interesting because Torch Dynamo is only looking at the bytecode, which is the PyTorch Python code. If people are familiar with training for machine learning, there is also the backward, which is deduced from the forward graph. But for PyTorch, it's done through this thing called AutoGrad tape, and it's done inside the dispatcher of PyTorch. So, and it's in C++. So Dynamo, even though it's very powerful, it's a bytecode inspector, so it doesn't see the C++ part of things. And that's why we need AOT AutoGrad to capture the backward of the graph through the Torch dispatcher C++ tracing. Yeah, so I'm explaining why there is then yet another component called AOT AutoGrad, capturing the backward graph, and Dynamo cannot trace into C++, and that's why we introduced AOT AutoGrad. And this component was co-designed with the Torch dispatcher component, the core dispatcher component of PyTorch. Very complicated, but just want to show that This is actually one of the value proposition of the P2 front end. Like a lot of people outside, it would be very, very hard for them to figure out how to get the backward graph because it's kind of implied. It's almost like tracing through the PyTorch framework code. You don't see that from the user level code, but we solved that problem. So the value proposition of AOT autograd is more than getting the backward graph. So there are other things that are also done at the dispatcher C++ code level. For example, we do operator decomposition, we do functionalization, and we also support like automatic mixed precision, functor transformation like VMAP, grad functions, tensor subclasses. So all of these advanced PyTorch features that's kind of hidden, encoded to Torch dispatcher, those things now, like with AOT autograd, us, the front end, is able to compose very well with them. All right, so I want to just recap on the front end part. So there is the forward graph, which is captured by Torch Dynamo by looking at the bytecode, and we do partial graphs, we do guard, and we do just in-time recapturing if guard fails. And then there is the backward part if you want to support training, and that's the AOT autograd component, and that's mainly dealing with the C++ part of the Torch dispatcher code within the PyTorch framework. All right, so the last component I want to introduce on the P2 stack is Torch inductor. So I want to say, like, even though P2 exists because we figure out the graph capture mechanism, but capturing graphs doesn't change performance, right? So the main value proposition of introducing a compiler is to improve performance. And the performance improvement aspect actually comes from the Torch inductor. So you can consider Torch inductor as more like a ML optimizing compiler. Actually, I would characterize it as a graph compiler. All right, so inductor principle, so we actually made a few design choices up front. So number one is the compiler is designed for PyTorch. So we're not taking like arbitrary compiler and then just slap it onto PyTorch. We look at the PyTorch op semantics and design it from like a very matching design. So for example, the tricky things like in-place updates or strided tensors or dynamic shape, those things are considered in the, I mean, they are the first class citizens in the design of this IR. Python first, that's really strange for me. Like I'm a traditional compiler person. I do like Fortran compiler or like Java or like all the traditional compiler. Like who wants to write a compiler in Python, right? So it turns out to be kind of a really important design choice for the ML world because number one, it allows us to develop really, really fast. And number two, it makes the system more hackable. And even today, you will see like a lot of new graduate students, they really know, there are way more people know Python than knowing C++. So I just want to put out there, this is perhaps one very different thing about ML compiler space is like nowadays, a lot of compilers in that space are written in Python. And breadth first is like what we see a lot of times, especially for research compiler, people, demonstrate, okay, maybe a BERT model or maybe llama model works, right? So it's like a model driven and just demonstrate like, these ops works. Versus for us, because PyTorch serves such a large ecosystem, we don't want something that only works for a few models. We want something that works like majority of the models. And it's easy to design a general purpose system and then specialize it, then design a specialized purpose system and then generalize it, right? So that's why in the beginning, we consider to really cover as many ops as possible. And then we can go into like these very important ops and we can specially optimize. That's a very practical consideration if we want to build a useful compiler. So, so for example, the breadth first approach is like from the IR design, we started to tackle all these tricky semantics because most of the models would use some aspect of these things. And there are some interesting aspects of inductor technology. I wouldn't go into details, but we do have an ASPLOS paper this year, 2024, which talks about details of these technologies. And maybe the only thing I want to highlight is early on, we made the design decision of the code gen part. Basically, we're talking about GPU generating the CUDA code part. We use Triton as our code generator, but a lot of the intelligence of which ops to fuse or how to tile things, those are done at the inductor level, at the graph compiler level. And we also use Triton template for certain things that's like a matmul or convolution. So this way we don't have to worry too much about the lower level, like different hardware generating code for already defined ops. And it allows us to build an end-to-end stack really fast. Okay, so I just want to say this is how we write the code about lowering from a torch op to the inductor IR. You don't have to understand that, but it's all Python code. And you can see like we do take care of like view offs and stuff. Yeah, so how do we lower from one IR to the other IR? So I want to point out that at the torch dynamo level, the IRs, each node represent an A10 op. Once we get into inductor, because we need to generate CUDA code, then we have to, at some point, lower to loop IR. So these are two very different ones. And as you can see, loop IR is lower level. So the way we lower that, because we have a huge op surface, so we use decomposition and we use compiler-specific lowerings for certain classes of operations. For example, all the element-wise would be lowered in one way, but you can customize it to like an add or some element-wise operation. Reduction is one category, gather scatter is another category. And also we are very practical, like there are certain lowerings that we even though there's a default way to lower them, but if we see there is like a clever shortcut, we would do those as well. And so we do handle dynamic shape and strides. I just want to point out dynamic shape is so hard to handle. Yeah, so this is like every year we have a session about the state of dynamic shape, and including the 24 PTC. So I just want to highlight like how do you think about performance, right? So what's interesting about torch inductor performance is the way we look at it is at a very high level. There is matmul and there is the memory bound operations like atom-wise, right? So matmul, we call them like heavy ops, and usually we think it's reasonable for a powerful like Top Gun developer, library writer to write the most efficient matmul operations. So it's fine. So we use cuBLAS, CutLAS, Triton template, all of those things. And inductor is mainly handling the long tail ops, fusion and cogen. But there are cases where we also venture into the matmul or the heavy op part, and I'll show you an example a little bit later. So that's the way to look at how things are. And I think a lot of the accelerator researchers probably are focusing on the heavy op category. So just want to give you like a sense of the kind of optimizations we implement, like we implement a lot of them. So this is for you guys if you want to do more research, like we already have a lot in inductor. And so just want to show you some data on does this approach work, right? To go breadth first, to go with like PyTorch native semantics and to go with Python first, right? So what's the performance we're getting? I would say this is probably the most comprehensive, like in terms of number of models showing geo-mean speedups. So what we are showing is speed up over eager by applying torch compile. And we have 3 benchmarks. There's a vision model, TIM, about 60, 70 models. Torchbench is a whole bunch of like paper, code on paper kind of research models. They're smaller, and then Hugging Face, which are transformer models. So altogether, it's 180 models. And actually, we track these speedups over eager through our nightly dashboard. And this one was captured like about half a year ago. And our geo-mean speedup for training is between 1.8 to 2x. It's geo-mean speedups. And actually, these different color is I'm showing like what we were presenting at PyTorch conference 23. So last October, that was about maybe 1.5 or 6x. And we're just showing we're continuing increasing it. And for inference, similar, actually we see higher speed up on inference. So it's between 1.85x to 2.23x. And we call these as out-of-box performance because it's kind of geo-mean over a lot of models versus a vertical benchmark like Llama. That would be a very different story. Okay. All right. So just want to recap a little bit on the PT2 stack. So before PT2 22, before our announcement, we have the eager approach. And then with PyTorch Conference 22, we announced like there is this Torch compile, and this is the technical stack with the two pieces in the front end and the graph compiler doing fusion. And then for CodeGen, we have Triton and we have CPP backend. And recently we also added a Halide backend as a reference backend for people who have their own ML hardware compiler to use this Halide backend as a reference point of doing your own backend. And PyTorch Conference 23, that's last year, we further extended the technical stack with P2 export. So this is to export out of Python because a lot of like embedded deployment or production deployment doesn't want to have Python into the picture. So we have two technologies one is called export and the other one is called the ahead of time form of inductor, AOT inductor. All right. Okay, so I want to spend maybe less than 10 minutes on the latest things that we presented to PyTorch conference that was September, mid of September. You might have noticed that so far, like for ML talk, I didn't talk about generative AI at all. And then in fact, we didn't talk about generative AI last year either. So 24, the theme is Torch compile for generative AI. So I just want to just contrast it, like the theme of PTC 23, the headline features are still very feature focused, like how do we introduce dynamic shape, export AOTI, and even like how do we bring compile into NumPy, right? So, and basically the way you look at the messaging is that last PTC 23, we're really talking about compile as a general purpose technology that kind of, we have a really interesting analogy. It's like we're raising the performance floor for most, so that's the out-of-box experience, versus in PTC 24 this year, we're talking about actually for generative AI, which is kind of like, usually we talk about Llama, like a really important model. So we say that's the performance ceiling for a few, right? So how do we do that? There's a very interesting arc over there. So I want people to go back to like a year ago. Like this is actually for real, it's our journey. Like a year ago, that's within the year of ChatGPT and all of that. So a lot of us was like disoriented, right? So, and it's true that at the time in 2023, if you want to claim slowdown on LLM models, the best way to do that is probably to build your own bespoke LLM systems and write custom kernels. So, and this is actually, it makes a lot of sense because LM is large foundational model, like one model that serves all the purposes. So if you just have one model or some variation of one model, it really makes a lot of sense to specialize just economically, right? And there is also like, not only it makes sense, it's sometimes it's necessary because everybody wants to claim something to be the first. It's a very hotly contended area. So it's kind of an arms race. And so whatever is fastest, you do that. And also because actually quantization is super important for LLMs, for the compute bandwidth. And a lot of times the existing like PyTorch framework like doesn't have, because these features are so new for those new hardware, we don't have very good support for these ops. So people have no choice but to write their quantized whatever FP8 linear layer, right? So there is a lot of reason for writing these custom kernels. And also because when you think about LM, they're like, you can deploy them in very different cases. Like training is like super, super large scale. And then you have like inference on the device, like very small glasses, and then on your desktop, right? So these wide range of requirements all require some specialization. So because of that, and I think there is another reason, like this area is so hot, so all the smart talents all go there and they're so capable, then they can build their own system. And that's what they did. So we saw a lot of single purpose ML frameworks, and they are either not related to PyTorch at all, or they use PyTorch just superficially, and then basically they write everything, almost everything as custom ops. So it is really threatening the ecosystem of PyTorch. So what do we do, right? So, and in fact, we were thinking like, Torch compile is a general purpose thing. Like now there are all these specialized LLMs and they are pretty capable of writing their highly performing custom kernels, like what would be the role of torch compile? So I think after a year, we figured out our path. At least we figured out some part of our path. So before I go into that, I just want to show you where we are in terms of torch compile for generative AI. Um, so number one, we are tracking like GitHub repos that are newly created over the last 12 months. And over 4,000 of them are compile enabled. In fact, newer repos are more geared towards the generative AI field. We have seen very strong reception on flex attention and GPT fast, both are torch compile based from the LLM community. And actually, PyTorch strategy for like overly specialized LLM system is to push our story out in terms of PyTorch native LLM solution, meaning that purely PyTorch, no custom kernels, like let us show you what's the performance we can get. And we have this triplet called Torch Titan for LLM training, Torch Tune for fine tuning, and Torch Chat for inference. And all of them are using Torch compile because they don't use custom kernels, they use torch compile to achieve the SOTA level performance. We are also bringing compile to ML users. So we have recent collaboration with Hugging Face, Transformer library, and they identified 17 top encoder-decoder models. And we are working with them right now. 16 out of 17 of them have been torch compile enabled. And these are just some examples of the ones that people recognize. We also started to see compile being used, adopted by startups. So Together AI, SGLang, Answer AI, and those are the examples. So those are very promising. And I want to show one quote from Together AI, where they say that the compile's value proposition is really to automate many performance critical optimizations. And I really love the last part that highlighted democratizing high performance LLM deployment. If you think about the value proposition of PyTorch, this is what PyTorch does, democratizing the system so everybody has access to a system instead of building everything from scratch. So then let me just explain how do we find our space into generative AI. It's still like a long way to go, but it just show you some intuitions. But actually the intuition is we actually realize in the past we have been focusing out-of-box experiences like long tail, geo-mean speedups, but for LM, because of the specialization, we really need to focus on a new user demographics. We call them power performance users. So those users are so capable that they never shy away from writing custom kernels or build system by themselves. And they don't care about how fast we are overeager. The only thing they care about is how fast are we against SOTA performance. So that requires a very different thinking on the kind of optimizations we do, or even the kind of measurement we do and whom do we compare against. So the question is like, then how do you entice power users to use compile, right? If they can write their own stuff. So we have 3 strategies. Number 1 is to provide a unique value that power users cannot resist. Number 2 is we really need to measure against the SOTA performance. And oftentimes this is not just compile, but you have to combine a couple of technologies together, including changing the model code. We call that vertical optimization. And the third one is we don't want to take away power users' ability to customize and control. So we basically, it's like, if you want to customize, you can customize. So we still make sure they have that capability. So let me give you example for each of them. The first one is called flex attention. And this one, I think everyone knows, like in theory, attention is all you need. But in practice, there are so many different variations of flash attention. And before flex attention, actually, what people do is they copy over flash attention, Trident kernel or maybe CUDA kernel, and then they start to modify. And it's a painstaking process, and a lot of people don't have that skill to do it. So that is no longer the case. We introduced this API called Flex Attention. It has a very intuitive interface. So it has QKV, which people understand. And then we have a way to customize your Flex Attention by defining a skull mode function that is kind of applied to each element. And with that, and underneath, if you invoke torch compile, what it does is that we have a very performing flash attention kernel inside inductor. And we have a way to mechanically generate customized flex attention based on score mod function. And with that, actually, we are able to generate a lot of the customized version. And with we see 90% of the performance if you really write them, or in some cases we see we are even better performing. So this is actually really the best of both worlds, which is like the flexibility or expressiveness of PyTorch and also the performance of flash attention. So ever since we released this, there was like very enthusiastic response from the community. And we even see like within Meta, like some of the fair researchers started to use this. All right, so the second example is GPT-Fast. So this is to show like how do we get SOTA performance purely with PyTorch native APIs and optimize it vertically. So I want to show that with a vertical optimized PyTorch native LM inference recipe, you can easily get 10x speedups over eager. And so for example, for GPT-Fast, we use compile, we use quantization, speculative decoding, tensor parallelism. And this code base is super simple because we do see a lot of people like to copy code over and then start to modify. And if it's too complicated, people don't understand and they wouldn't be able to massage it in the way that they want. And so simplicity and no custom kernels, those are the key for it easy for people to adopt. And we are also keeping GPT-Fast up to date. So we released GPT-Fast last November. And since then, we have added Llama 2, Llama 3, Llama 3.1, mixture model or MOE models. And we continue to incorporate the latest technology into the GPT-Fast repo. So what about the performance? So actually GPT-Fast claims to be very performing with small batch sizes. We're working on the large batch sizes. To give you some examples, actually, the way to measure performance is tokens per second. And of course, you can always scale, like if you use more GPU, it will be bigger. So I'm only showing for either a single GPU performance, tokens per second, or a single node, like 8 GPUs, like intra-node kind of communication. So this shows the performance we have for Llama 3.1, 7B, and 70B performance. All right, so the last strategy example is to give power users ability to customize. So the primary way for power users to customize their PyTorch experience is through PyTorch extension point. So we do make sure that compile support these extension point. For example, we introduce user-defined Triton kernels. We can use it together with compile, not a problem. This is since 2.3 release. We have better support for custom autograd function. This is also what we often see the power user uses to do their custom backward functions. Mutable custom ops, we see that in, I think, VLM code base, torchbind-based custom class, that we also see from VLM code base for representing quantized data types. Okay. All right, so the last part of the talk, I'll try to do it in 5 minutes so we can have some time for questions. Yeah, so because this is a university, I want to show like why do you care, PT2? Like what can we bring for you guys, right? So the number one thing is actually I want researchers to use PT2 infrastructure, especially our benchmarking infrastructure. So let me show you. So I do paper reviews as well, and I often see out the evaluation is really crappy. Like usually it's 5 models, no more than 10 models. But if you use PyTorch benchmark, we have 180 models, and we are also adding vertical benchmarks like llama models and stuff like that, right? So there's a more extensive coverage for validating your idea. I already showed these are the 180 models that we are tracking. And we are not only just tracking speedups, we also track pass rate, super important. If optimization is overly specialized for a particular model, it may not actually work correctly for others. We also track peak performance. This is super, super important, especially for larger models or if you're running on desktop situation or distributed scenario and compile time. Those are what users really care about. And these are the information for the benchmark infra. If you search, you could find our performance dashboard. And yeah, we can also test different backends. You can add your own backend to the script. Let's see. Yeah, so we do see like on the academic research, there are many more mistakes in terms of when people are evaluating performance. We want to call out for that. So one way to see is if you look at our ASPLOS paper, there is an appendix section, and that explains to how we were evaluating. So, and if you read that, you will also see like what are the important things. So for example, oh, are you comparing against max autotune? If your approach is the autotune approach, then better compare with another one that uses autotune. Or what is the data type you're using? For inference, are you using freezing? And also, are you enabling photograph? So because those are best practices for the baseline. And this shows our performance dashboard. So this is what we run every night, and we track all these metrics here, and it's all publicly accessible. And we have training and inference different types and different benchmarks, as well as like different hardware. So we recently added the ARM hardware, but there is also like NVIDIA GPU, AMD GPU, and so on and so forth. Okay. All right. So, and these talk about some of the new LLM models that's been added to our benchmark target, and including GPT-Fast. All right. So, and I also want to highlight, like, as I mentioned, like a lot of times when you do research on training, it's harder to get the training graph. So, and this is another thing the PD2 front end has already solved for you guys, because we have OU to autograph, so we are able to faithfully capture the graphs that the eager mode is executing. And I would say like training is increasingly important. Like with LM, like I would say way more than 50% of flops are on major companies are spent on kind of LM pre-training. All right, so the last one, I know there are people who are doing software hardware co-design, designing your own accelerators. I want to say that if you do a backend hooking up with Inductor, the benefit you have if you care about PyTorch models is that we significantly reduce the op surface that you have to care about. So if you integrate at the eager level, there are like over 1,000 ops, and if you remove the overload, it might still be several hundreds of ops that you have to care about for like a complete coverage. But because we do a lot of decomposition and normalization after the graph getting into inductor level, so inductor IR only contains like 50 ops or 50 IRs. And this is similar to if you integrate your system as a Triton backend. So Triton IR is very close to almost like one-on-one mapping to inductor. So either inductor backend or Triton backend, you would have like at least an order of magnitude less number of ops that you have to worry about. Yeah, and so that's just for hardware compiler researchers to consider what is the right point of integration to reduce your ops surface. All right, so I think I'm gonna wrap up. What's the key message? I think I just want people to remember this large flywheel. It's generated by Meta AI, powered by PyTorch, I would say. So I would say PyTorch has been this like large flywheel that we're building, and the same for the PyTorch compiler. And PyTorch has always been taking like a systematic approach to delivering sustainable performance, as opposed to if you write one custom kernel. And this is the same approach that Torch Compile is doing. And even though I was talking about generative AI, but I want to point out that it's the same stack we're building. It's still, when we are targeting generative AI, we're still enhancing Inductor, we're still enhancing the front end, we're still enhancing Triton, right? So before generative AI, we do these things. After generative AI, we're still doing this thing. So this is how we are approaching about PyTorch performance. And the 24, the new story is, in addition to targeting out-of-box performance, we also started to target really power users, and that requires a different thinking. And this message actually is for power users to consider compile and also PyTorch native approach as part of their generative AI solution. So I guess the last message I want to give is, if I look back on the success of PyTorch, or more recently on this kind of the journey of the compiler team go through in terms of making 2.0 happen, I do see there's one persistent thread, which is the entire design of PyTorch is very user focused. So we're trying to figure out like what user really want instead of like have the technology in front of the user. So that's something that's very different from like a PhD research writing papers. And I think that's the essence of building a useful compiler. All right, so we have 5 more minutes.
So,
you want to clap or a question? Okay. Questions?
the way we do this, because we're hybrid, this is where the microphone is. I'm going to come also over here.
Mm-hmm.
Let's start with questions in the room, and I will take a look at the chat here and call them out as needed. So let's start over there.
Yeah.
Thank you for the talk. So I have a question about reproducibility of the compiler, because they are concerned about the security of the ML supply chain and so on. So in terms of the bytecode generated by the PyTorch compiler, for different architecture, are they reproducible and exactly byte by byte for different compiler run?
I see. So the question is about the reproducibility of the graphs that the PyTorch compiler capture. So are they differing run by run? They could be differing run by run, but it's not a reproducibility problem because when we capture graph, we use a tracing technology. So you might be taking this true path versus that false path based on the runtime configuration or the data. So that's why it's changing. But with the same data and the same model, it should be the same. And graph capture usually does not depend on the hardware platform, unless there's something about the device. If the code has something about the device, then it might vary a little bit. And I don't see them as a security problem because basically what we have is just basically the model code is already open. And PyTorch code itself is also open, so I don't see a security risk there.
Okay, so before we take your question, let me call on the Zoomers again. If you have any questions, please type in the chat or raise your hand. So let's go with you in the meantime.
Okay.
I understand that bytecode.
Yeah.
Whenever it's not able to generate bytecode for a certain piece of code that is something that's not in its capability, it creates graph breaks.
Yeah.
So my question is, how does this work when it comes across, let's say, NCCL collective communication operations? How are such asynchronous operations being taken care of, especially when we're looking at a distributed training setting where
that's such a good question. Yeah. So the question is, when dynamo capture graphs, how do we deal with the NICO level communication operation? So actually, when we do the tracing, it's not the NICO communication we're seeing, it's the PyTorch distributed collectives, so C10D operations. So we have an effort of functionalize the C10D collectives to make them traceable. So a lot of what we're doing for distributed is to make sure the distributed framework code are traceable, or we can represent it into the inductor code. So if we are able to represent, for example, the all gather, all scatter, that kind of thing, the underlying implementation could be a NICO implementation or could be something else. So we don't directly look at the NICO ops there. Yeah, but it is a challenge. This is actually the area that the inductor team is investing, because in the past we have been focusing on optimizing compute, and before we just graph break on communication, we don't include communication ops into the graph. So this year we're starting to first capture communication ops and represent it in a way that's meaningful into the inductor graph. We're still exploring how to optimize in terms of the thinking is to overlap compute with communication instead of reordering communication, because reordering communication is very tricky, could introduce deadlocks. So we're looking at that, yeah.
Or like passes.
So forward is one way of looking at thing, and then we have the backward AUTOGRAD, AOT AUTOGRAD. We have a technology called compiled autograd, which would combine all the backward graph into one. That might introduce another level of tracing. Yeah, but I don't think you have to worry about that. The only implication would be compile time, because every tracing could, yeah, or code compile time at least. Yeah.
Okay, so let's do you next. We work our way over here and then we start there again. Let's start there.
Okay.
A picture of all the highly specialized kernel parts.
Yeah.
So people are trying to write some CUDA code,
Mm-hmm.
but we use colors.
Yeah.
I think there are many ways there. So such as you may determine by human if you are going to use shared memory, how will you take care of cache, choose on both sides?
Yeah.
Those things, I think, how can compiler always those things to choose the right strategy?
I see. So we have an auto tuner. So number one, the actual kernel code gen, we rely on Triton. And there's a huge community of people trying to improve Triton kernel performance. And I would say Triton heavy op code gen is maybe still has some way to go to compare with Cutlass. So people are working on that. And we do have auto tune for like selecting the best configuration there. And recently, actually, what we see is right now we see a lot of people writing custom kernels. So we are compiling a benchmark of Triton custom kernels versus the PyTorch native implementation, and we put Torch compile on top of it and try to measure the performance. So recently we did the Liger library from LinkedIn, and we see more than 50% of the time the compiler generated performance is on par or better. But the peak memory were way worse because we look at their code, it's like, oh, they were chunking. When you have a big op, they actually do tiling chunking kind of optimization, cross contribute, that kind of thing. We didn't have that optimization. So now we're working on it. So what we're doing is we do feel power users, they are at the cutting edge of what would get you the most performance. And we try to build a flywheel between what they do and what the compiler can do. So we learn from them. And if it makes sense, we incorporate into the compiler. So that's the way we actually there will always be people writing custom kernels. What we don't want to happen is unhealthy proliferation of custom kernels over a long time. And then there's a lot of, like, it's very hard to maintain, right? So once there is a certain way of doing things, and we can really build it into the compiler. It's easier for everyone.
Your
Yeah.
question?
Yes, I have two questions.
Mhm.
The first question is besides the GPU and also Meta's hardware, what's your plan to support other types of AI chips?
Yeah.
For example, Graph GPU, Nova. I think what kind of approaches you are going to use to make the PyTorch more popular? Probably this company will also think about how to use the PyTorch, right? Probably have some conversations with them. I want to understand what's the difficulties when they port the PyTorch to their hardware. Yeah. Right. So that's one question. The second question is that when we scale the AI infrastructure, how do you plan to support the scalability? Right. For example, when you compare the models and how you scale the workload across multiple machines.
Yeah. Okay. So the first question is, how does PT2 support heterogeneous hardware beyond the most popular ones and the Meta's own hardware? So number one, PyTorch's position, we don't choose winners. We support our strategy is to support the most popular ones. And if you look at how the hardware integration happened, it's actually all the vendors integrating with us, but we do provide the platform to make it easier. So for example, initially we developed the inductor to focus on NVIDIA GPU because that's the most popular one and we also care about it. And that initial version, actually, we have a lot of things that's CUDA specific. It's not intentional. It's just like when we were writing, I was thinking about CUDA, so device is CUDA. And AMD GPU start to integrate and Intel CPU start to integrate. And then obviously they hit this device being like, why is it built in, like written as CUDA or parameters CUDA? So what they did, they generalized device and generalized the parameterization. So once they did that, then for subsequent hardware, it's a lot easier for them. So far even with MTI, like we don't have to do a lot. Like we basically, MTI team would integrate with us, and they are like kind of third-party backend, so they're not even in the PyTorch core. So what I would say for other hardware, I think the accelerator hardware needs to prove their value. When you say like, how do we increase adoption? The hardware is not the main thing. It's the ML researchers. So that's where I say like our views sometimes are skewed by our technology. Like in the first picture, I said like, a compiler is at the center of the thing. No, it's not. Compiler is not. The same for hardware. So whoever is the winner, they will integrate. We'll make sure it's.
They build a hardware,
Mhm.
they have to build their own ecosystem. So instead of ask them to build their own ecosystem, how about we just have an environment to support them so they can just join the PyTorch ecosystem.
So you already can do that because we solved the graph capture problem. So if, for example, if your accelerator can do a Triton backend, you can reuse most of the P2 stack, right? But there's a question mark whether the accelerator hardware is suitable for representation on Triton. So that's why we built the Halide backend as another reference backend for people to explore with. Yeah, but I think PyTorch is very neutral in terms of hardware. It's like whoever is popular, people want it, we'll make sure they are support. And also because of our dominance, and those companies would also work closely with us. So most of the work are done by the hardware vendors.
Okay.
And the second question, the third one is the scaling, right? So number one, I want to say for very, very large scale scaling, the crux is not on the compiler side. I mean, just be realistic. It's more fault tolerance, like just distributed technology. And I would say like Llama training or LM pre-training, that scale is very, very different from everything else. So totally fine to build a customized system. But there is one thing about compiler technology in those systems, like just in time is good for ease of use, but it's also a kind of variable in terms of production. Anything can go wrong. So right now we're exploiting ahead of time technologies to reduce the complexity of introducing compiler just in time into the system. And another thing we see is actually also in production in the more moderate scale, compile time is a huge issue. We didn't even think of it as a big problem, but it keeps on coming up. So now we have good solution for like caching solution for warm compile time, but even that is not enough because a lot of what we see in production is they do experimentation. So there's not much that they can cache in a run. So actually next year, one of our focus is to reduce the code compilation time. And what I want to say is like, that's just where the user-centric approach, like if we're connected to people who are really using our system, these problems would show up. Like as long as we are humble enough to listen to them, we'll have very relevant problems to solve.
Great. So let's, in the interest of time, we'll close it here. You can ask your question right after you can walk
Yeah,
out.
I will be around. So
Peng is around, and Peng is around until including lunch and things like that.
including
So
lunch, yes.
if anyone wants to talk to her, you can join that. But before we leave, let's thank Peng again for a great presentation.
Thank you.
Thank you.
All right, thank you. We are ending here.